All right, ladies and gentlemen, class recording has started. So, on Friday, we got started in on the next section dealing with, next section in chapter 16 that starts taking the charges that we introduced in 16.1 and doing something with them. What do we do with these charges? Great. They attract, the opposite charges attract, the like charges repel. Great. What does that mean? What do we do with them? And so we started off our discussion with the idea of gravitational potential energy. That, you know, we move something up, it falls back down, gravitational potential, into kinetic, blah, 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 blah. But we said those topics are very similar conceptually to the idea of electrical potential energy, where gravitational potential energy deals with things, where things are in relation to the ground or a source of gravity. Electrical potential energy deals with where things are in relation to other charges. And we talked about moving this charge around in the electric field, that if we take this positive charge and move it closer to these net positive charges over here on the left, right, that increases their electrical potential energy because they don't like being there. And so they move away from one another. And as they move away, the electrical potential energy decreases and the kinetic energy increases. Just like when we talk about gravitational potential energy, but now we're talking about where things are in relation to charges versus relation to the ground. Right? And so we said that there are three ways that we can increase the electrical potential energy of an object. If we take positives and move them closer to other positives, that will increase their electrical potential energy. If we take negatives and move them closer to other negatives, that will also increase their electrical potential energy. And then if we take positives and negatives and move them farther apart, that increases potential energy because they try to get back together. This idea of electrical potential energy gets us into the idea of, okay, how do we get this object to do what we want it to do, right? Give it the ability to move or change other stuff, energy. Right? How much energy that particle gains depends on some other factors, especially how strong is the electric field that we're moving this particle in. If we take this positively charged yellow particle and move it closer to these 5 positive charges, it's going to have more electrical potential energy than if we move it closer to these 3 positive charges. That ability to increase energy, or how much does the energy increase, we refer to as the potential difference or the voltage of an electric field. How much energy do charges gain as they move in this electric field? Okay? And I believe we talked about, this is how we describe or define voltage, right? We talk about it as terms of energy per charge, right? That's why it's joules per coulomb. How much energy do the charges gain versus how much charge there actually is. Okay? And we refer to that as the volts. Okay? What does that mean? Well, that takes us to this picture, which you guys have a copy of in your notes, and we will make some notes, or we will describe some things as these charges move through this circuit. So this is a circuit, which we'll talk more in detail about starting tomorrow. Okay? And the battery here is what we refer to as a source of potential difference. It gives charges that are in this circuit energy. So, there are electrons that exist within this circuit, and as they move through the battery, because of a chemical reaction that occurs inside of it, creates an electric field. And these electrons, I call them green, okay, as they move through the battery, they end up gaining electric potential energy. That's what a voltage source does. It increases the electric potential energy of the charges. Notice this green electron, it ends up at the negative terminal of this battery. Is this a high potential energy state? We said that to increase the electrical potential energy of charges, we can move positives closer to positives, or we can move negatives closer to negatives. So the battery forces these electrons through the battery, and they end up by the negative terminal. Do they like being here? No. Will they stay there on their own? No. And then what happens is the battery then releases those electrons into the circuit. Usually the wire is a conductor, right? And conductors allow charges to move through them. And so these charges start to move. Boom, like that. Okay? Like we talked about, as those charges, as the negative charges move away from the negative terminal of the battery, potential energy decreases. But if potential energy decreases, what do we generally see happen? If potential energy decreases, kinetic energy increases. Because of what, Maura? The whole idea of conservation of energy, right? That if one type of energy goes down, another type of energy goes up. Okay? And these charges start to move. Good there? They continue to move throughout the circuit, right? And then they get through whatever we maybe attach to that circuit, like this light bulb. The light bulb also converts potential energy, but it converts it into something different. The light bulb converts the potential energy into light and heat. But the amount of light and heat that are generated by the light bulb is equal to the amount of potential energy, or electrical potential energy, that the electrons lose. Why? Conservation of energy. Depending on what else we put in this circuit, we could convert that electrical potential energy into sound if we connect it to like a speaker, or we can connect it like to like a motorized car or something and turn it into kinetic energy, whatever. All that does, the light bulb in this case, or anything else that we put in this circuit, is it takes electrical potential energy and converts it into other stuff. The whole time that these electrons are flowing through the circuit, they are moving away from the negative terminal of the battery and closer to the positive terminal of the battery. This is causing their potential energy, their electric potential energy, to decrease, and finally it ends up right back here, right? By the time the electrons complete their trip of the circuit, they will have transformed all of the electrical potential energy that the battery gave them into other things. That's what the battery does. It provides energy to the electrons, and then those electrons travel through the circuit and they turn that potential energy into other kinds of energy. Now that those electrons have made one full trip and are back at that positive part of the battery, positive terminal, they like being there. Will they move from that spot? Not on their own, right? But we can make them move if we do what to those electrons?
Like remove the battery?
We can move, not remove the battery. What do we say the battery does?
Like transfer the current?
No. The battery does what to those electrons? Together.
Work.
And it gives them energy, right? Those electrons won't move from the positive terminal of the battery unless we make them move from the positive terminal of the battery by doing work, right? The battery does work and provides those energy, or provides those electrons with energy. potential difference, or the voltage of the battery, measures the difference in electrical potential energy at each terminal. So how much work is done on each electron? That's the potential difference, or the voltage of the battery. Okay? The potential difference, or the voltage source, does work on charges and increases their energy. That's what the voltage does. The voltage source. Okay? All right. Are we okay with the concept of voltage or potential difference? Talks about how much energy are these charges gaining as they move through the electric field. Now, once we've increased the energy, right, the energy is going to be transferred into other forms, as long as we can get that energy of the electron way over here to the light bulb. So we have to move the electron. The movement of those charges is called current, defined as the rate at which electric charges pass through a certain area of a conductor. Current is defined as the rate at which electric charges pass through a certain area of a conductor. This picture down at the bottom illustrates the idea of current, but it can be a little misleading depending on how we define current. So, a couple of things you need to know about current. First, current is the movement of charge carriers. Could be positive, could be negative. Which ones are easier for us to move, the positives or the negatives? Negatives. Why? Did you just guess a word?
No, because I think it's like in the outer.
What part of the atom are we talking about?
The energy levels.
What part of the atom are we talking about? Andrew, you want to help?
The electrons.
The electrons,
As
right?
they move around the nucleus, are easy to transport than a proton.
The electrons are easier for us to move because of those things, right? They're outside the nucleus, especially which electrons?
Valence.
The valence electrons, right? So generally, right, current is usually the flow of electrons. Could be the flow of positive charges, but it's a lot easier for us to move electrons around than it is for us to move protons especially, but that doesn't happen, right? Protons don't move. It would be like positively charged atoms if we were talking about that. But usually it's the flow of electrons, okay? If you look at your definition, okay? If you look at your sorry, let's do this one, okay? But in order to get those charges to move, we have to make them move, right? An electric field provides an electric force to those charges and makes them move from one place to another. So there has to be an electric field that causes those charges to start moving. And that's how we get current. Okay? Electrons don't just move on their own. They'll move in response to other negative charges or other positive charges. If we want to get them to move in a certain way, we set up the other positives and negatives to get them moved from here to there. Okay? Now, if you go back to your definition of current, just a couple lines above where you were just writing, we said it's defined as the rate of charge movement, right? What is it? The rate at which electric charges pass through a certain area of a conductor, right? So, how much current we have is going to depend on two things. First, it's going to depend on how much charge we have. But second, because we were define it as a rate, when we talk about something being a rate, we said that there's a certain factor that is built in. When we talk about something being a rate, what factor are we talking about? Time, right? So, Rhea, when we talk about not that picture, this picture, okay? Current is defined as delta Q over delta T, right? The Q we've actually ran into in the last section. We used Q to represent the amount of charge. So, the rate of charge movement defines current, okay? Delta Q over delta T. How much charge over how much time? When we look at the units, the SI unit that we use for current is the ampere. Ampere is a derived unit. It depends on two other units. In this case, coulombs and seconds. Because coulomb is what we use to measure what? What do we measure in coulombs? Charge. And what do we measure in seconds? Time, right? So charge per time. How many how many charges are flowing for every second that goes by? Yes, Ian?
What do those triangles mean?
The triangle is a Greek letter. It means delta. It represents change, okay? If you just write Q over T, that'll be fine. Charge over time, okay? It's actually the change in charge over the change in time, but that's not important for your understanding of the concept.
So in our packet, where it says SI unit equals amp, like, do you have to put the current equals I or the amp fee? How you pronounce that? Ampere.
So for that, for I, you would put Q over T, right? Okay, you don't have to put the triangles if you don't want to, just put Q over T, okay? And then, when it says 1A, right, that A represents ampere, so 1 ampere is defined as 1 coulomb for every 1 second.
Okay.
So charge over time.
And the SI unit would be the ampere.
SI unit would be ampere, yep, capital letter A. All right, so if you flip it over to the top of the back page, apparently I forgot to put this in my presentation, right? But 1 ampere is the movement of 1 coulomb of charge for every 1 second that goes by. So if you at the top of page 3, it says 1 ampere is defined, or is the movement of 1 coulomb of charge for every 1 second that goes by. And a coulomb, remember, a coulomb is actually 1 electron is a very small amount of a coulomb. So we're talking about a large number of electrons to carry that charge. Okay? Good there? Current comes in 2 forms. Direct current, or DC, as its name would suggest, is electrons only flowing in one direction. So just like this circuit that we looked at earlier, electrons are always going to flow from the negative terminal of the battery back over to the positive terminal of the battery. And that's why direct current is generally supplied by batteries and certain types of generators. But there's only, it's current because it's moving of charges, but those charges only flow in one direction. However, there is another way that we can get charge to move, but it results in charges sort of jumping back and forth, side to side, side to side, side to side. And we refer to that as AC, or alternating current. If you've ever been to the Science Center before, they have a little bike that you sit on, and you like pedal, and you can get the lights to light up. Maybe you've seen it somewhere else, okay, right? But anyway, as you turn those wheels, okay, you are actually turning a coil of wire inside of a magnet. And that magnet causes the electrons to move, right? Negatives are repelled from other negatives, attracted to positives. We'll find out next week that magnets are really just a special case of the positive and negative charge, attraction and repulsion. So if we take that coil of wire, right, a small loop of wire, and just spin it around in a magnet, the charges will start to flow. They don't flow only in one direction, though. They actually sort of jump back and forth, side, 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 side. Still movement, just not the same. Okay? Good there? Okay. These terms that we have discussed, voltage, current, DC, AC, these are things that I'm assuming you guys have sort of heard before, right, but maybe aren't real familiar with. Okay? So the rest of page 3 is a good way to distinguish and contrast these terms. So let's start off with something that we have labeled as low current and low voltage. So, right, we label something low current, low voltage. Okay? What does current tell us about? What do we say that current tells us about? Andrew, you want to answer, or you just
The
stretch?
flow of electrons.
The flow of electrons, or how many electrons there are, right?
Yeah.
But what does voltage tell us about?
The energy of the electrons.
The energy of the electron. Have you done this before, or did you just like pick that up?
What do you mean?
Oh, never mind. So,
Was that a pun based on the backpacks?
yeah, right. Do you do electronic stuff or no, or just okay?
Like how do you
Yeah,
I don't know. I just guessed, and it seemed like the most logical guess.
it's a good guess. It's right. Okay. So when we talk about low current and low voltage, okay, current tells us about how many electrons there are. Voltage tells us about how much energy those charges have. So something that's low current and low voltage means that there are not very many electrons, and each one of those electrons doesn't carry very much energy. Okay? All right, good there? So let's jump down then to the very bottom, because it's easier to make that jump down to the very last one, right? Okay. Oh, too far. Okay. So high current and high voltage. First, if something has high current, what is that going to mean? How many electrons are we talking about now? A lot, right? And if you notice, the number of people, right, has increased, okay? But because it's high voltage, oops, sorry, probably should have put that up, okay? If it's high voltage, that means that those charges, there are a lot of them, but how much energy do they have? A lot or a little?
Wow.
A lot, right? This is the dangerous stuff. High current, high voltage. Okay? There's a lot of electrons, and each one of those electrons carries a lot of energy. Now, how much total energy we're getting depends on the combination of the two. So, we can talk about something that has low current but high voltage, right? If something has low current, what does that mean?
There's not a lot of them.
There's not a lot of
Electrons?
electrons, but if it's high voltage, those electrons carry a lot of energy. The end result is that we get kind of a moderate or medium amount of energy that is being carried total. Each electron carries a lot of energy, but if there aren't that many of them, you don't get a total amount, right? On the other hand, right, high current but low voltage, right? If it's high current, that means what?
There are a lot of electrons, but they don't have much energy.
Good. If you want to make an analogy, right? If you think about it like in the old school, do you want to make an analogy for us, Andrew? Or
Like what do you mean?
do you want to something that would like illustrate this principle like in real life, or do you want me to do it?
Let me think for a quick second.
If you want.
You are at a grocery store, and as you and your friends each have a shopping cart each, stuff, but there are more people, but not a lot of stuff.
Okay.
Then you get 3 cars with a lot of stuff.
So let's go with this, okay? The number of shopping carts would represent
Electrons.
the current, right? So if you have a lot of shopping carts, that would be a high current, right?
Yeah.
But if you don't put very much stuff in each shopping cart, that would be a low voltage,
Yeah.
right? How many groceries are you going to end up getting if you have a lot of shopping carts but don't put a lot in them?
Not a lot.
Not a lot of groceries,
But
right?
when you get both stuff, you have only a few and a lot of stuff in it.
But if you only have one shopping cart, right,
Yeah.
even if you fill it up kind of a lot, do you get a lot of groceries?
No.
Because you only got one shopping cart,
But you
right?
still get more than to get a bunch of shopping carts and put like one item in it.
Right, and that could depend on how many shopping carts you have and how much stuff you put in each
Yeah,
one, right?
like
if you have 50 shopping carts, but you put only one thing in each shopping cart,
But it would be 1 bag of goldfish.
yeah. But still, if you get 50 bags of goldfish, it's kind of a lot of groceries, right?
Yeah, but what if you
I'm saying it's a sliding scale.
yeah, but what if you put what if you put like 1,000 peppermint patties in the one?
But that's still not quite a lot of groceries, though,
Yeah.
right? All right. So, just to illustrate this principle, okay? I haven't opened these containers yet. Hold on, we're not done. We still have like 10 minutes left. Something left. All right. So,
What does that have to do with it?
in my hand, I have 3 different batteries. Some of them aren't open yet, but whatever. Okay. This is a AAA battery. This is a AA battery. And this is a C battery. Okay? You can lick these all you want. Nothing's going to happen. Okay? So, each one of these batteries, if you check the side, has a voltage of 1.5 volts. Okay? What I want you guys to discuss in your small groups, there is something that makes these batteries similar, and there's something that makes them different. Discuss. Go.
Isn't that true though? Like if you touch your tongue to
Okay, so
Yeah. Really?
the fact that all 3 of these batteries have the same voltage, what is that telling you about them? That as electrons pass through these batteries, they are gaining the same amount of energy. Okay, that's the voltage. What's different about them?
Some have more electrons than the others.
So what would be different about them? They would produce a different.
Like one would be, what would
How about use what? They would produce a different current, right? This C battery, right? How much current is this C battery going to produce? More than these, right? They all produce electrons that have the same energy. They do the same amount of work on each electron, but how many electrons they release is different. Okay? A 9-volt battery. I don't have a 9-volt battery with me. Do you guys know which 9 volts are? The square ones? The rectangular ones? Okay? Trey, if you put your tongue on a 9-volt battery, what happens?
Zapped you.
It does zap you a little
Does it
bit.
hurt?
Okay? It gives you a little shock. Mora, I'm not telling you to go home and put your tongue on a 9-volt battery. Okay? And I would like to make sure that it gets on recording, right? That I'm not telling Mora to go home and put her tongue on a 9-volt battery. But if you do, okay?
Go to the emergency room.
No. We won't take you to the emergency room, okay?
I'll go in the song.
It gives you a little bit of a shock. The fact that it is a 9-volt battery, this battery is only a 1.5 volt battery. Okay? The fact that a 9-volt battery is 9 volts, what is that telling you? Andrew?
It has high voltage.
High voltage, meaning that it does what to electrons?
It gives them a lot of energy.
It gives them a lot of energy. But how big is a 9-volt battery?
Small.
It's pretty small, right? I mean, it's a little bit bigger than this, but size-wise, it's about the same as this.
So it's low current but high voltage.
Low current but high voltage. Now, a battery from a car. Okay? Have you ever seen a car battery before? Right? It's about yay big. It's like a shoebox-ish. A car battery is a 12-volt battery.
So if you lick that, it's blue.
Don't lick that one, Mora. Right here. Mora, I am specifically telling you not to go home and lick a 12-volt car battery. You would hurt yourself.
I just like whip it out of my car.
So, hey, hold on. If you have ever seen somebody jump a car before, have you ever seen anybody jump start a car? Okay. The jumper cables. So you attach to the battery of one car, okay, and they're conductors, so they take the energy and flow it to the battery of your car. Right now, if you take the jumper cables, they're attached to the car battery, okay.
Yeah, you clack them together.
If you hold the plastic part, don't hold the metal part, okay. If holding the plastic part, if you touch the metal parts together, you will see a pretty big spark. Okay, because first it's a 12-volt battery, okay, meaning a lot of energy. But if you look at the size, right, a car battery is significantly bigger than this. So a car battery is high voltage, but also high current. Okay, that will put you in the hospital. Okay, yes, Jay.
There's this guy that did like a practical joke where he acted like his car was down, and then he'd clack them together, and then he'd like pass out and have the people like. Yeah,
now, to make our jump.
Practical joke.
Yeah, this is not very joking. All right, but to make our jump to tomorrow, okay? Here. Oh, but not here. Here. This outlet, it's in the table, and all those outlets that are in that table and in the wall, okay? Those outlets are 120 volts. Okay?
When I was little, I put tweezers in an outlet and I got shot.
Yeah, I bet you did. Okay.
There's still like a mark on the outlet.
Yeah, I bet there is. All right, so, hey, wait, hold on. Hey, wait, we're almost done. Yeah, I bet, more, I bet there is a mark. So,
There's a mark in here too.
the problem, all right, listen, okay? The problem that we'll discuss tomorrow. The charges that come out of that outlet have a huge amount of energy. It's 120 volts, okay? Hold on. Easy. 120 volts, but we plug in to that outlet everything from that pencil sharpener that's in the back of the room to like an electric drill to a refrigerator. Not all of those things need the same amount of energy. So there has to be some way for us to get the correct amount of energy to each of those things, even though we plug them into the same outlet. And we will talk about that tomorrow.
We just talked about it before. It's going to be okay.